In this video, we're going to solve this problem twice, one in the case of no friction and one in the case of kinetic friction. Now, we could solve it with the static friction case. We could solve it for things like the coefficient of static friction, tension in the rope, things like that. And you are welcome to do that, but I'm going to solve it for the kinetic friction case because what I'm going to do is get some intuition as to the acceleration of this system in both cases. So let's do free body diagrams of these objects. For M1, I've got M1G, I've got the normal force, and I've got a tension force, which that's all I have because there's no friction. For M2, coordinate system, sorry. For this object, my coordinate system, these are going to be my positive x and y directions, where this is x and this is y. Because this is a coupled system, I'm going to couple it mathematically by coupling my coordinate systems. Here's M2G, here's tension, and what I mean by coupling the coordinate systems is here are my positive directions, but this is my x-axis and this is my y-axis, right? My x-axis is pointing down. I do that because a motion in the x direction for M1, and specifically a positive motion in the x direction, will now correspond to a positive motion in the x direction for M2. If this is the first time you've seen that, that might seem a little strange. Hey, can you just do that with your coordinate systems? Yes, you can. Your coordinate systems are yours to control. So because this system is physically coupled, we want to couple it mathematically. The way I do that is to define my coordinate systems such that a motion in one is symbolized the same way in the other. All right, so this thing I think is probably obvious is going to accelerate downwards if there's no friction, definitely. So what can I do here? Well, I can do Newton's second law, and in either direction for this one, I only have one direction that really matters here. There's nothing happening in the y direction. But in this case, maybe we can see that there would be somewhat pointless to do it in the y direction. I mean, you certainly can. You're going to get that the normal force is equal to M1G, but I'm not going to be able to do anything with that information. So let's just skip it. You can do it if you want, that's fine, but I'm going to do it in the x direction. It's equal to MA sub x. Oh, I should put M1A sub x, right? And so, well, let me keep going here. So what do I get? In the positive direction, I get tension is equal to M1A sub x. And if I do Newton's second law on the second object, sum of the forces in the x direction is now M2A sub x. Now, you might ask yourself, why am I not subscripting the accelerations, right? This should be the acceleration of block 1, so maybe I should subscript this with a 1. This should be the acceleration of block 2, so maybe I should subscript this with a 2. Well, sure, but if these things are tied together, if one moves in one way, the other is going to move in the same way. This is like a truck and a trailer. Hopefully, they accelerate at the same rate. They move at the same rate. They undergo the same displacements because they are coupled. You also might notice that I'm not subscripting the tension. This is pretty standard in Physics 1 courses. We assume that the string is inextensible and massless and that the pulley is frictionless and massless. If all that is the case, then I find the same tension everywhere in the string. If that's not the case, right, if this was a chain and I couldn't neglect the mass of the chain, then I would definitely get a difference in tension as I move along the rope because the mass above that point is different and the mass below that point is different. But in this case, we'll make the standard assumptions, inextensible massless string, which means that these tensions are the same, and then because they're coupled, the accelerations are the same. That makes my job pretty easy. If I unpack these forces in the positive direction, I've got M2G. In the negative direction, I've got minus T. That's equal to M2A sub x. All right. What do we want to solve for? Well, usually we solve for tensions and the accelerations. I'm going to go ahead and solve for the accelerations here. Those are the two unknowns I should point out. I know what the masses are. Those are given. I always know what little g is. So what I don't know are the tensions and the accelerations. So I've got two equations, two unknowns. I'm in pretty good shape. Let me go ahead and solve for the accelerations first. To do that, I'm going to solve each of these for the tensions. This is already done. Let's do this one for the tension. Tension is going to equal m2g minus m2a sub x. Now I have two equations that are both equal to the same thing, right? Good old transitive property. If a is equal to b and b is equal to c, then certainly a is equal to c, and that enables me to eliminate the tension quickly. So I get m1a sub x is equal to m2g minus m2a sub x. Collect like terms. m1ax plus m2ax equals m2g. Factor out ax times m1 plus m2 equals m2g. Therefore, ax is equal to this term. This is how I like to write it. m2 over m1 plus m2g. So let's talk about this result. What do we expect this to be? Well, if I just look at the free body diagram of m2, right, I don't expect it to be accelerating at g. If I look at this free body diagram, then I expect it to accelerate downward at g because there's nothing else. The only thing acting on it is gravity, and that's the definition of free fall. Only gravity acts on it. That gives you an acceleration of g downwards. But that's not the only thing acting on it. I've got a tension force. I do expect it to accelerate downwards, but the net force is now something less than gravity. Gravity minus the tension force. So I expect the acceleration to be less than g, which the way that would be possible is if this coefficient is less than g. And is it? Well, if masses are all positive, and they are, then yes it is, because the denominator of this expression will always be bigger than the numerator. m2 divided by m2 plus something is going to be less than 1. And so I get an acceleration here less than g, which is what I would expect. How much less than g? Well, that depends on the masses. If m2 is really big, then m2 dominates, well, there's only m2 in the numerator. m2 dominates in the denominator, and m2 plus 1 is basically m2, and I get basically 1 out of this, and the acceleration approaches g. If m1 is really big, then m1 dominates in the denominator, and m2 over this is kind of like m2 over m1, right? m1 plus m2 is kind of m1. And so then I get my acceleration goes less and less, a smaller rate. So that you can see the physics here. It depends on the ratio of the masses, or at least the ratio of mass 2 to this additive term. And then that is a fraction of g. There's no way I should point out that you're going to get something larger than g here. To do that, you'd have to have some sort of applied force in the downwards direction. You could have that in some situations, but in this case, there's no way possible that you can do that. So you're always going to get something less than g. In the next video, we're going to look at a different situation where I have friction. But we're going to hang on to this because I want to come back and compare the answers we get to see what we can learn from that.